Humans are extremely curious at the observations of nature, and visualizing transparent fluids is a particularly frustrating task, where its structure and motion are invisible to the naked eye. Schlieren imaging overcomes this challenge. A Schlieren image reveals the density changes within a fluid, and a traditional system layout has a light source directed to knife edge. Light bends as it travels through fluids of varying density, so the knife edge blocks half of the deflected light rays, causing light in dark areas, forming a Schlieren image. Small-scale experiments dating back to the 17th century can depict the thermal plume of a candle. The intricate optical setup typically consists of expensive parabolic mirrors, a point light source, and a camera with a knife edge set at the focal length. Now in the information age, with the availability of cameras and high processing power, Schlieren imaging has evolved where large complex flow phenomena have been captured. This is only possible with background-oriented Schlieren, BOS. BOS reduces complexity by removing the optical components and harnesses image processing. The setup consists of only a camera and a suitable background pattern, and 2016 results from NASA reveal high-resolution images of shockwaves surrounding the T-38 supersonic aircraft, with just a high-speed camera facing a desert background. The 1994 experiment with motion camera Schlieren could not capture the change in density equivalent to the clarity of BOS. Starting in the early 2000s, this relatively new technique has been explored in various fields. Experiments take advantage of the ability to capture large atypical objects, the simplified setup, and the potential to extend analysis, not only flow visualization, but also quantitative measurements of density, pressure, and temperature. The German Aerospace Centre has visualized helicopter tip vortices and blade interaction using mountain terrain background, and even shockwaves from explosive and transonic wind tunnel tests have been achieved. BOS acts similar to the optical illusions of mirage and heat haze. You may have seen this while driving on a hot summer's day. Parts of the road appear as pools of water or mirror-like and reflects a distant object. The effect can also be seen from the exhaust of a jet engine, and in this image, distant trees appear to be distorted when looking through the hotter, less dense air. As mentioned, light bends when it enters an object of different density. The BOS setup does not use a knife edge to block deflected light rays. Instead, BOS captures light rays from the background image distortion of two images. One image without the object and another image with the object. The difference in the two reveals the light ray deflection. Typically, a dot background pattern is used. And from these deflections, image processing can generate the overall light ray displacement field. And combining this with ray tracing theory, the refractive index and density field computed resulted in pseudo-Schlieren images. Therefore, this project aims to bring a robust and flexible visualization capability using the background-oriented Schlieren technique to Loughborough University. A packaged software-hardware solution should be intuitive and accessible for use within the Aeronautical and Automotive department. BOS has less hardware than traditional Schlieren imaging, but it is dependent on a dedicated software program. For a typical 2D BOS setup, the software can be broken down into three core sections: displacement, refractive index, and density. As mentioned, the software must first interpret two images, a reference image and a measurement image. The image is divided into smaller areas, and by comparing the location of the reference image dotted pattern with the measurement image dotted pattern, the displacement is quantified. This technique is known as cross-correlation. By considering the physical parameters, an elliptical differential equation is formed, Poisson's equation. This facilitates computation of the refractive index field. And finally, the Gladstone-Dale constant relates refractive index to density. Recent experiments adopt gradient and variational-based algorithms, where they interpret the light intensity of reference and measurement images rather than the light deflection. These can achieve comparable results, though these are less explored and usually more complex. The BOS technique is easy to implement, easy to modify for specific applications, and no two BOS experiments are the same. There is a variety of camera types from CCD to DSLR, monochromatic camera, high-speed and endoscopic, which have captured both 2D and 3D flows. Similarly, background patterns vary, including dotted, wavelet, colour, natural and retrospective patterns. Though for simplicity, these are predominantly dotted for easier image processing. The illumination of the background has been achieved with LED light as well as fluorescent, laser and sunlight. Despite these differences, to obtain the best results with the greatest accuracy, most experiments conclude the camera resolution and lens focal length should be maximised. The depth of view should include both the Schlieren object and the background, and light rays should be made as parallel as possible. In 2015, Verso and Libeson tackled multiple medium BOS by analysing a stratified liquid. And to encourage further BOS investigations, they granted open access to their software solution, and I have explored their software procedure. Their test case has a cell line solution of 4 distinct densities. The setup captured 2D planar images using the typical Z-type configuration, where the camera, object, and background are along a single axis. The background was backlit with a white light source illuminating randomly distributed black dots on an A4 transparent sheet. And the stratified liquid was placed in a glass tank. The difference in the rate of light ray deflection by air, glass, and the stratified solution would need to be considered. So, a calibration stage was implemented before the core analysis. They used the computing environment MATLAB, the main programming language for aeronautical and automotive students at Free University. And breaking down their methodology enabled understanding of a potential software approach for this project. The program is segmented and draws from outsourced functions to support its solution. Notably, to find the dotted pattern displacements, the program takes existing software which was previously designed to analyse images captured by the PIV technique, particle image velocimetry. And there are also 2 methods to solve the platonic equation. Initially, when running the program with the BOS images, the results did not match those from the 2015 paper. So an investigation into the sources of the problems were undertaken, which was supported by an insight from the program co-author, Professor Alex Libeson. For example, an error caused the gradient of displacements to fall to 0 at certain points. The elliptical equation could not be solved, so changing the matrix referencing corrected the error. Debugging the code systematically allowed errors as small as incorrect mathematical operators to be identified. And now the program offers comparable results. The 4 levels of differing liquid density are detected, and computation of this density profile is calculated. This software has provided a solid insight into the possibilities of the project, where it is evident that the displacement field calculation using cross-correlation is refined, but the refractive index solution using a discretized Poisson equation is less developed and more prone to errors. There is also a large number of setup parameters, which are difficult to locate and change. My software solution should improve on their approach to Poisson's equation and have an easy-to-understand image processing interface that can process a variety of images. From this, 5 core objectives have been recognised. Firstly, by extending evaluations of the latest research and alternative practices, a better understanding of the BOS technique can be made throughout the project. BOS software is the heart of the project, therefore designing and validating the software is the primary focus. An approach with MATLAB will attempt to resolve images taken by a simple Z-type configuration with a monochromatic camera. Initially by capturing simple flows, such as a candle plume. The intention is to work on the software and hardware section concurrently to continuously exploit problems and drive towards a robust and flexible system. And to consolidate findings from the practical setup, a tiered equipment comparison will be undertaken, aiming to contrast image quality capability with 3 different budgets. Finally, the project will be closed with a technical report and oral presentation. Background-oriented Schlieren at Loughborough University will expand flow visualization experiments by taking advantage of its simple configuration and versatility and its potential to quantitative analysis. Development and testing of a modular MATLAB program with a short-distance camera configuration will enable a BOS capability and facilitate future extensions, such as 3D flow visualization and absolute quantitative measurements. Thank you.